Hey everyone, I am very excited to get to share with you what I have in this series of videos. I've come across a different way of thinking about the attention mechanism in transformers, and I have found it to be a better mental model. I think it gives some better metaphors for what's going on. I suspect it could be an easier way to introduce the concepts to someone new to attention. And I think it fairly naturally explains some of the different varieties of attention we have: multi-head attention, multi-head latent attention, group query attention. And then I think there's an opportunity here too, and maybe these already exist, but we can create some better fun visualizations for what's going on in attention beyond just the ones we have today. So is this idea new? This part I'm embarrassed by. I spent probably a good week and a half manically working out all of the insights in these slides, thinking I was onto something amazing. I actually had GPT kind of encouraging me along the way too, like, oh, that's incredible. That makes so much more sense. Wow. I've learned, like, don't trust compliments from an AI, maybe. Anyway, all that only to find that everything I'm going to share with you, you can find in the introduction to this paper right here from the Interpretability team at Anthropic. And these are the foundational concepts of a field of research called mechanistic interpretability, which seeks to reverse engineer the transformer to try to figure out as much as possible what's going on inside of it, which makes sense that maybe I should be reading this more, right? If my job is to try and make these concepts accessible, then maybe reading interpretability research could be helpful for that. Been missing out. So this term was coined by Chris Olah, who was at OpenAI and then is one of the co-founders of Anthropic. So discovering this, coming upon this, was pretty bad for my ego, but who cares about that? It's great news because it means that these ideas are how some very intelligent people, some very skilled researchers think on a daily basis about how attention works. So I think we've just been missing out, and I'm really glad to have the opportunity to kind of take some of these concepts and use them for accessibility, I guess. And I think maybe that's what I do, accessibility research instead of interpretability. It all starts with this one little detail of the attention equations, which is that the output matrix has a per head output matrix, output projection. And when you make that small adjustment, that one little I, then a lot changes, and a lot of this intuition kind of naturally falls out. It's incredible. So we'll start there. And then one of the things that's really nice once you split the output matrix into per head versions is that it becomes very clear that the query key and value output are two distinct independent processes that are happening in parallel. And I think that's good for understanding attention. And then something really cool is that you also see that the value projection matrix for a given head and the output projection matrix for that head are just or could be viewed as a low rank decomposition of some larger matrix, WVO. And similarly, on the query key side, you can view those as a low rank decomposition of a larger matrix, QK. These two matrices, I think, are really valuable for understanding what's happening in attention. And something I want to cover and argue for in this series, I think query key value output, those terms, we've kind of overloaded them. They have multiple meanings. We use them in multiple contexts. And I think it creates some confusion. And I think there's kind of an opportunity here to alleviate some of that by adopting some new terms for some of these quantities that don't really exist in our normal attention equations. And so I want to suggest that this, borrowing from graph neural networks and some recent work in combining graph neural networks and transformers, MI is the message that a token wants to send or will send through head I. And then down here, also borrowing language that I've seen in Crisolo's work and other interpretability works, we have PI, the attention pattern, which token X will use to look at the tokens in the sequence and determine which messages are relevant. A couple more things I know I want to cover, and maybe more stuff will come up as I work on the series. There is this concept from interpretability called the residual stream, and I love it. I think it's such a great shift in perspective on what's happening with the tokens through the layers. So we'll talk about that. And then I think there's some cool visualizations we can do where right now it's kind of helpful for giving people some intuition about attention. We have these illustrations where we can show like this particular head seems to be attending from the object of a verb back to the verb. Pretty cool, right? So it's mapping this kind of understandable linguistic concept. And with what's cool about the messages is that they are in model space. And we can actually kind of look inside them and try to interpret them a little bit and actually see what each token, not just the attention between tokens, but also what kind of message the token is trying to send. So I'll talk more about that. So something very important to understand here is that this sort of merging of value output and merging of query key, the purpose is that this provides some helpful conceptualization of attention. It is not necessarily a good idea to implement it. That's not the point here. No one should go change their PyTorch code based on these insights. And I think an objection that would be easy to make is like, oh, well, this is a terrible idea. If you implement this, it's more memory and compute. There's a reason we decompose them. Yeah, absolutely. So that's not what this is about. It's about the concept. And then also, you could argue that if you teach someone in terms of just these two matrices, then you do eventually need to work down back towards queries, keys, values, outputs, because you want to explain how it's actually implemented. So you could argue it's like, well, this is kind of circuitous. It just gets you back to where we already are. But I think it's still a valuable mindset for all of us. And then I think it might be a more natural progression for a new learner to go through to start here and then see how it feels fairly natural to take one of these matrices and say, okay, these are low rank. They're over parameterized. We want to decompose them. So how do we want to decompose them? We have options. And you can kind of motivate the query key value output perspective from that, as well as motivate the other attention implementations. All right, so let's get started with the one little detail that I think if nothing else, if you don't like any of this stuff, any of this matrix merging, I think you'll agree that at least splitting the output into per head projection matrices is a valuable insight. So let's start there. These are all of the equations from Attention is All You Need that describe the attention mechanism, multi-head attention, as well as the illustration over here to the side. And there's a detail in here that is oriented towards making this all efficient on the GPU that is kind of obscuring something really important. And to see what that is, notice how for each of the projection matrices, we've got this little I subscript that indicates that we've got one of these per head. But then you get to the output matrix and we're missing it. There's no I. And instead we've got this number of heads term in the dimensions of that matrix. And that's how it looks on the GPU. We've got this one giant WO matrix. It never needs to be split during the computation. It's learned as one giant matrix. However, there very much is mathematically a per head output matrix. And the reason for this confusion, I guess, is the concat step. So concatenating matrices kind of breaks my normal intuition for how matrix multiplication works. So really, when you concatenate stuff on one side of this multiplication, there's kind of an implied concatenation on the other side, where you must be concatenating a bunch of smaller matrices as well. So if you go to the illustration where we've got WO on top, there's just sort of this implied stacking of the per head output matrices. If we want to go more conceptual, get a better intuitive understanding of what's going on here, we can replace these concatenations with a sum. So it's a much nicer way to express this, right? We just take each of the heads, and these are the outputs of the heads, and we're multiplying them against their corresponding, that's funny, I thought I fixed that, against their corresponding output matrix. And we can express that as like multiply each of them together, sum them up over the total number of heads. And that's pretty straightforward, right? It's the giant monolithic output matrix is kind of a little bit of a black box, but really it's just per head projections summed together. No weighting, no complex recombination, just a simple sum. So this is what it would look like to redo the illustration with that summation instead of a concatenation. And what's nice is that when you look here, we've got like a per head output. And then in order to finish our explanation of attention, we have to concatenate all the heads. We've got to bring in the topic of multi-head attention in order to finish the process. But if you break it out into a sum, you recognize that each head is really its own independent process. And they each produce their own output and they're just summed together. So what's great about that is that we can look at just a single head. If we want to explain how attention works or think about it, we don't need to think about multiple heads. We can just think about the details of a single head, and we know that there's multiple heads running, right? You get added together. I'll give you my honest kind of day-to-day mental picture of how attention works. I think of the embeddings for a sequence of words, and let's say we're going to apply attention between the final token and all the others. So we're going to project onto the query and key space, right? And then we'll take our query and we'll multiply it against each of the keys, get the dot product. All that goes into the softmax to normalize it. And then we get scores. And so notice, it's the multi-head part. It's kind of, I know it's in there. I know it's like, these are blocked, these are chunked into heads, but it's kind of hard to think about that. It's more convenient just to think about it from a matrix perspective. But then once we get to here, the softmax, it starts to break down a bit, right? Scores, what does that mean? And then we'll project the tokens onto the value space as well. And we know that the scores somehow get applied to the values, which are also broken up in heads. Kind of vague on what that is. And the output of that, though, is I can understand the output. We get this final embedding back in model space, which, sorry, I'm using GPT-2 dimensions. I've been using that as an example for some of my illustrations lately. So, oh yes, and then also these are the projection matrices, but hopefully that was obvious. And it's not per head, that's like the entire layer. Okay, yep, and I think of it as an adjustment because we know it gets added back to the input. That's the residual connection. So you add the output of attention back on top of the input, and then you get your output. So it's okay, but it's a bummer that I can't keep track of what happens in between here. And I'm sure I could if I was a little more disciplined about it, but we can make it easier. If you just do a single head perspective, then instead of the big square matrices, we can think about them in terms of their head sizes. So we know GPT-2 head size is 64. So we project down into a smaller space for the head, and we do that for both. And then same dot product thing, but now because we're only looking at a single head, the scores are just a nice simple array. We've got one score for every token. And that means that we can take these down to the values and we apply them to each of the values and sum that up. And then, yeah, last time I didn't even put the output matrix in there, right? I just kind of leapt past that. But here, it doesn't feel too hard to do that. It's like, okay, we've weighted the values with the scores. We've got our final output for this head. We're going to reproject it back into the model space. And then from there, so now I've got like a complete accurate picture, right, of a single head. And then from there, it's just, okay, there's 12 heads. So each one's doing a different specialty, and they all get summed up. The outputs all get summed up. They get added to the residual again, and we get our final result. So not only do I feel like this is easier to understand, but it also kind of highlights that we've got this embedding for each head that's getting stacked on top of the input instead of just one single one. So that's kind of cool. It's great that splitting the output matrix makes it easier for Chris to remember how attention works. That's really nice. But there's some exciting implications that come out once you make that change to the math. Something about the original illustrations that I've always had kind of a tough time with is that the queries, keys, and values are all shown going into attention. And the full equation for attention is this. We do softmax of queries and keys times the values. And that's what's considered attention. But I think most of us, and I see this in papers, really it's like attention, this feels like attention. Queries times keys. That's where we're scoring the different words to see how relevant they are. And I think this is often denoted alpha as the scores, or even just the word scores. And then we multiply those by the values. So the fact that the values step is in there, it just feels a little out of place. So we can draw something that's equivalent, where we put the attention scoring as a separate block and the values come in afterwards. So we've got the values here, scores over here, and then when lines intersect in the original illustrations from the Transformers paper, that means there's multiplication happening. So we're multiplying, for this head, we're multiplying the scores times the values together, and then we multiply by the output projection for this head. There's a number of different illustrations out there besides the original one for attention, and there's some that maintain this kind of QKV, and then there's others that look more like this, where they do route the values around. And if you look at the original paper, when it actually looks inside this block here, the purple block, it does actually kind of look like this. Okay, but once you draw it like this, and we have what's distinct here is what you won't find usually in illustrations is this right here, right? We can draw this, but to go past that, we got to concatenate. But now that we've got the per head output matrix in there, it starts to become apparent that there's really two things going on here, right? There's the attention scoring, and then there's this other channel here that's really independent. And it feels to me like it would make more sense to do the output projection first and then score the embeddings and take the sum of those. The reason that we have this, the QKV, is that concatenation step again. We need to apply the scores to the values before we concatenate. At least I think that's it. I assume it's like another GPU efficiency thing. But again, we're playing with the math, so we don't have to abide by those rules, and we can switch the order around. We can apply the value projection matrix and then the output projection matrix. So over here, we've got the scores, and then over here we've got, and we multiply those two things together and we get our output embedding for this attention head. You already know where this is going, and even though this was discovered or has been known about by many researchers for years, coming to this point in the math, writing out X, W, V, W, O, that's pretty sloppy, I'm sorry. That was an incredible moment. It's like, what is that? That's crazy. Has anyone noticed this before? Like, I've been staring at LoRa and DeepSeek long enough to recognize, like, okay, that's obviously a matrix decomposition. This is some larger matrix that's being represented there. And then, what the heck is this? Like, what is the result of these terms? It's not O. O is the per head output. And it's not Z. That's the other one we have, which is in value space and has the scores applied. We don't have a variable for it. Even in the interpretability work, I think it's typically just left as, well, actually it would be more like XWVO. I think there may be like a variable R for result, but it has the score applied. So I think this one might be up for grabs. And I shared this with GPT, right? This is where I'm looking at it and going like, wow, look what I discovered. Oh, that's incredible, Chris. What a major contribution. Like, what should we call it? Like, I think we should call it messages, because it captures the fact that this is how tokens send and receive info, and it borrows from graph neural networks. So that was a very helpful insight there. Kind of later discovered like, okay, yeah, no, that is a term that's used. It's typically used to describe the values instead of the reprojected values. But yeah, all right, let's see what is this quantity really. So for a given head I, this is the value vector, but it's been, we have it for every token, and it's been reprojected to model space by the per head output matrix. And it hasn't had attention scoring applied yet. So this variable is mi. It is the set of messages that the tokens in the sequence want to send to the rest of the model through this head. Part of what had me so excited to see these messages was that they are in model space, the same space as the vocabulary, which means that we can compare these message vectors to words. So I've tried doing that, and as long as you are careful about the layer normalizations, then sure enough, some of these messages have meaning. You can read them, which is really cool. So here's an example sentence. The baseball player hit a home run is the word we're predicting. And we can look at the word baseball and see that these different heads are extracting baseball related terms. We can look at hit and see that we've got some, not just like synonyms of baseball, but things that are a little more contextual. Like once you hit the ball, you get to walk or run, and you might hit a strike or a ball. And hitting maybe implies scoring. Maybe you hit the pitcher. And then we can kind of see how it's copying knowledge forward through the tokens. So even though this is just the letter A here, the word A, it has, by layer 7, 10, and 11, it's had the chance to absorb information from other tokens in earlier layers. And so we can see that it's delivering information like strike and baseball and shortstop. This means that now, in the same way that we've got a way to view the per head, per token attention, we've got the per head, per message contents. And another thing we can do with this that's kind of cool is because we have the projection matrix for messages in model space, we can also just throw arbitrary words at it from the vocabulary and see what comes out the other side. We can even throw the entire vocabulary at it and see if there's kind of a consistent pattern to what kinds of information the head extracts. So I think this by no means solves interpretability. I think there's a lot of complex information being passed on by attention, and there's probably specific things that looking at the word similarity can tell us versus not, but still really cool. Seems like a great, satisfying educational tool. And I'm excited to see what else we can do with it. And there's probably some research out there that it's done something similar. So looking forward to finding that as well, seeing what we can kind of reproduce with this approach. And then let's look at the patterns on the other side, the query key side of things, because we can do some similar things there. Given that we can merge the value and output matrices into a larger one, I think it's natural to wonder, can we do the same thing with the queries and keys? And yes, we can. So currently we take a query vector, project it onto query space, and then do the same with the sequence tokens to get the keys, multiply those together to get the attention, logits, and we can rearrange that to put the projection matrices together, and then of course combine those and get our attention head pattern matrix. So we can do some of the same kind of analysis with this. I think what's different, so we can already look at where heads are placing attention, right? But maybe something a little different about this is that we can do a more, maybe call it speculative analysis, where we can project a word onto the pattern matrix, get its pattern, compare that to the vocabulary, and see what would this head like to attend to if it were present. Whereas when we do the attention scores, we have to, whatever it attends to has to be in the sentence, right? So one of the ways we can use that is looking at the position information. So if you project the pattern for, let's say, like a central position encoding vector, then you can compare the pattern to every position in the encoding layer, and we can see where the head is inherently biased, what positions in the sequence it's biased towards. And we see like a lot of like intense bias towards the first token in the sequence. Or I think it would be kind of fun to see since it's a decoder model, if it was putting like a ton of bias on like the next token, right? It's like if someone would just show me the next token, then I would do such a great job at predicting it. Let's see, what else can we look at with this? Yeah, and then in the same way, you can project the vocabulary onto the message projection. You can also project the vocabulary onto the pattern projection. And doing that, I think I saw some clear patterns in like, this head seems to be very focused on geography, and this one seems very focused on math and science. So when there's a clear sort of semantic role for the head, then you can see that pretty clearly by analyzing the pattern projection matrix. So it's been maybe 6 months now since I recorded that video and wrote this series. Probably good that I waited a while to publish it because the ideas have had more time to marinate, figure out what's useful, what's not. So I would say for sure this first point is huge. I hope this becomes common knowledge, common way of thinking. It's just so much easier, I find, to think about attention when you think about it in terms of the individual heads acting independently. And to do that, being able to break apart the output matrix into the per head, into the individual head projections is key. So being able to think about it in terms of query key and value output. And then the fact that you can fuse the matrices, pretty useful insight, something I've been playing with. And then probably the most valuable thing, maybe second to the output head, is this concept of the residual stream, which I'm not sure I got to talk about in this video. Definitely want to come back to it. But it's this idea that really what we think of as the token vector is more like this communication bus that the model uses to send messages between components. So that is huge. Another one that I just think is, I really hope that we all start to think in more of those terms. I'm not a huge fan of residual stream. I wish it was something different, but it's this kind of communication bus. Let's see. Yeah, and then the part that I'm less sure about is trying to rename these matrices. So I've definitely backed off on that, and in the work I've been doing since, I just write VO and QK. I think probably the primary motivation for renaming them was so that we had a variable, a letter to use for these. And I haven't used those as much. And I think that kind of brings up another important point to clarify. Sorry about my voice here. Comparing these vectors to the vocabulary to try to figure out what words they contain. That's more the exception than the norm. It's rare that you'll find semantic meaning in these vectors, which actually is really cool because if they're not carrying semantic information, if they're not carrying word meaning, what are they carrying? So it kind of suggests that it's more like metadata or instructions to the rest of the model. So it's more complex, more interesting, I think, than just kind of updating the meaning of the word. Really, it's the feed-forward networks seem to be more responsible for changing the meaning of the word. Yeah, I'd say renaming, maybe if there is a value in that, it's probably more for education. I would be kind of curious to see if presenting attention in terms of these 2 matrices instead of 4 might be a good way to start. But when you're doing like efficiency architecture research, I mean, something interesting is that when you're looking at a matrix, a weight matrix, and trying to understand what it's doing, decomposing it is actually a really good way to get some deeper insight into what it's trying to do. So looking at the separate value and output matrix and query and key matrix can be more insightful than looking at the fused form. So yeah, we'll see. Definitely don't want to push on that too hard if it's not actually valuable. But definitely want to come back, clarify some of this stuff some more, talk about the residual stream. Visualizations would be cool. It'd be awesome if I could team up with a more seasoned interpretability researcher, I think, to make sure the insights that I'm conveying there are good ones. But yeah, fun stuff. Till next time.